Okay, so the first thing is, this is in contrast what we usually call Cartesian or Euclidean coordinates. So Cartesian, sometimes Euclidean coordinates are regular old x and y. So by a coordinate system, I just mean a way of locating a point. Okay, that's what a coordinate system gives you. It's a way of putting a point in space. This gives you a way of figuring out where some point in two-dimensional space is. And the way that you think about it is, you've never even thought about this in a long time. What you're given when you're given Cartesian coordinates is a certain amount of direction to move over here in the x direction, and then a certain amount of direction to move this way, which is the y direction. And where you end up is the point x, y. So you can think about this in either way, but the idea is you go this far in the x direction and this far in the y direction, and where you land, that's what the coordinate system is telling you. Literally just how to move in space to locate a point. In polar coordinates, we have a different way of uniquely assigning a set of numbers to every point in the plane. So the way that most people think of XY space, or Cartesian space, is chopped up into a grid. Not totally accurate to think of it this way, but you've got this grid. And when I give you an X and a Y coordinate, what I'm telling you is where you fall on this grid as you move left and right and up and down. So space is, I mean, graph paper in Cartesian coordinates made of little boxes for a reason. Count left, count up, figure out where you are, put a dot. In polar coordinates, we cut the plane up into a different type of background arrangement for locating points. Instead of using X and Y, which you can think of as being like right and up are the two directions that we can move, right? Left or right or up and down. Here we're going to use angle and radius. So R is going to be equal to a radius. Theta is going to be equal to an angle. And instead of locating a point by how far to the left or right we go and how far to the up or down we go, instead we're going to think about a graph that looks like this. The space is chopped up into a bunch of concentric circles that measure different radii. And then there's rays that go through it that correspond to different angles. Of course, the first question you might have is, why on earth would anybody do this? And the answer is, an unfortunate number of things in physical reality move in circular directions. So frequently, choosing a coordinate system comes from some problem that you're trying to study and the way that the problem you're studying is moving. Okay, so a point in this particular arrangement you can think of as looking like r theta. It's still a two-dimensional coordinate system. But now, the r is telling me which circle to use. R is 1, R is 2, R is 3, R is 4. So we still have an idea of 1, 2, 3, and 4. You can think of this as being a measure of the radius that we go out. And the theta tells us how far to rotate around the coordinate system. So this axis we think of as the 0 axis. So theta is equal to 0. For mathematicians, measure angle from the positive x-axis and rotate counterclockwise. Mathematicians do. Physicists don't always do that. Engineers don't always do that. Okay? A lot of coordinate systems in the physical sciences start at the positive y-axis and rotate in either direction, depending on what your discipline happens to be. For us, this is where angles are going to start, and positive angles are going to rotate counterclockwise. So positive angles rotate from the positive x-axis counterclockwise. An example, if I was given the point 2 pi over 4, this tells me which circle to be on, and that tells me how far to rotate. So 2 pi over 4 in polar coordinates corresponds to sliding over to the radius 2 circle and then spinning up until you're at the angle pi over 4. So that point right there is the point 2 pi over 4. Another example, how about the point? So there's some oddities of this system, right? Which is that points have, the same point can have multiple names, which is odd. That doesn't happen over here. Over here, every point has a unique name. If I give you two numbers and I say a point, you just go draw it. You don't have to worry that you've accidentally stumbled into a different number. Over here, you can think about what happens if I wrote down something like, what if I wrote down the point 2 minus 7 pi over 4? Well, that would say, if I wanted to plot that point, go to the circle of radius 2 and then rotate backwards by 7 pi over 4 degrees, right? So this point said go this way by pi over 4 degrees. This point says get on the circle radius 2 and go backwards 7 pi over 4 radians, which puts you at the same point. So rotating backwards by 7 pi over 4, the same as rotating forward by pi over 4, which is irritating. It means that this is literally the same object in space with two different names. That has to be dealt with when you're dealing with these rotational systems. We see this coming up in things like sine and cosine, right? They repeat every 2 pi. It's like here we've got an entire coordinate system that repeats every 2 pi. That's not the only weirdness of the system. Somebody could say, plot the point minus 2, 5 pi over 4. When you go backwards by 2 units, rotate to an angle of 5 pi over 4, and then do a radius of negative 2. 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 2 5 pi over 4 would be right here. You can think of this as being mark 1, and this as being radius 2. 2 5 pi over 4 would be here. So where is minus 2 5 pi over 4? Go out to this angle and then go the other direction. So you go backwards. We rotate to this angle, and then we travel backwards along the radius until we get to minus 2. That point right there, minus 2 5 pi over 4, which also happens to be the same as 2 pi over 4, and also 2 minus 7 pi over 4. That seems like a flaw in the coordinate system. But you have to deal with the fact, just like in sines and cosines, that you can shift by 2 pi and not change anything. It's part of what it means to like have a system built for rotations, so that you come back around to where you started. So it's a feature, not a bug, right? It's the way to think about this. Does that make sense? I think this, I know this is weird, but like this is the basic setup here, is that the way I like to do is I do, so I don't get confused with the idea that the radius puts me on the circle, but it doesn't tell me what direction to move. I like to think of angle first and then radius. Angle first and then radius would put me right here. Okay. So you might say, well, what can we do with it that we can't do with regular old Cartesian coordinates? So the first thing is, we can think of functions. So what we're going to do is we're going to define functions. It's not quite yet. So the idea of polar coordinates is that we can define functions where theta is the independent variable and r is equal to f of theta is the dependent variable. So these are functions where you think of the angle is moving like x, but instead of moving like x, where a function you slide down the x-axis and a function develops, here we rotate around the origin, and as we rotate, the radius changes, and that's how we get a curve out instead. Okay, so we're going to be looking at functions where we're thinking of angle as the input and radius as the output. Okay. An example. Plot r is equal to theta. That's about the simplest possible function, right? Y equals x is about the simplest function in Cartesian coordinates. R is equal to theta is about the simplest function in polar coordinates. So let's plot it. I can't plot anything without a handy table. You should anticipate already that oftentimes these functions will be trig functions, which are natural to evaluate on angles. And so having your unit circle memorized would be a good thing. Okay, so normally when you're plotting these things, it's typical to use unit circle angles because they're easy to compute. Most of you have them drilled in your heads in some way. So I'm going to pick some convenient thetas here, like 0. Maybe I'll do pi over 4, pi over 2, 3 pi over 4, and pi. I'm just going to pick some values. See what this function is doing. So f of theta, in this case it's just theta, gives you the same values back again. Remember, these are angles. These are radii. So when we plot, we have to plot with respect to the fact that these inputs tell us the angle to be at, and this tells us how far out to go. Okay, so it's not like plotting in the XY coordinate system. So this is how I would approach this. I would say, okay, I know theta is equal to 0 is along this line for the origin. If I go out at 0 angle, how far am I supposed to go in radius? 0. 0 radius means I'm at the origin always. Now, when I travel out in the pi over 4 direction, what's my radius supposed to be? Pi over 4, which is about 0.7 or something. 3.14 divided by 4, about 0.7. Okay, so pi over 4, pi over 4. But remember again, angle, radius. Now what? Pi over 2, pi over 2. Pi over 2 is an angle, puts us straight up. Pi over 2 is a number, puts us bigger than 1. 3.14 divided by 2 is like 1.6. So now I'm out here. If you plotted the points in between these, what you're going to get is this curve that is growing. As the angle moves, the curve sweeps out further and further, and so the radius keeps increasing as you get out. If you go all the way around to pi, now your radius is 3. I think 3. Yeah, 3.14 by the time you're out here, right? So all the way at pi, now you're not at 1.7, you're all the way out 1, 2, 3, all the way out here. Pi, pi, again, angle, radius. So this is a shape you would never be able to describe in Cartesian coordinates, right? It's a spiral. There's no natural way of writing spirals down in x and y coordinates. This is badly not a function with respect to x and y. As you keep sweeping out the angle, this thing will keep going around and around and around itself further each time. Okay? So when I talk about this system being natural for things where rotation is happening, this is what I mean, right? Graphs that rotate in this sense are very natural to describe in polar coordinates in a way that if you tried to do this in Cartesian coordinates, it would be a disaster. That said, there is a way to converge. And one of the common tools that we need to do is to be able to take points that we find in the Cartesian or in the polar system and figure out what their coordinates are in the XY system. So the way we do that is like this. If I have some point right here at r theta, and I wanted to know the x and y coordinates of the same point, Well, if I wanted to label this in x and y coordinates, I would need to know how far to go out in the x direction and how far to go up in the y direction, right? The x and y would tell me what the xy coordinates are, in the same way that the rotation theta and the stretch of the radius tell me what the coordinates are. So this triangle is the relationship that we need to use to figure out how to go back and forth between Cartesian coordinates and polar coordinates. Boy, that should look familiar. It's a right triangle, and it's a right triangle that looks an awful lot like the right triangle we use when we're doing either vector decomposition in a physics class, if you've seen that before, and most of you have seen that, like, have been beaten to death by that already, or when you're developing trig ratios. So the relationship here is, so there's a couple different relationships you can observe from this triangle. The first is that x squared plus y squared is equal to r squared. Pythagorean theorem holds. The next relationship that I see is there some relationship between, that gives me a connection between x and y and r. Is there a way to connect x and y to theta, which is opposite, adjacent, tangent. Tangent, so y over x is equal to the tangent of theta. Because in a right triangle, the ratio of the opposite side to the adjacent side is called the tangent of the angle, right? Okay, so that gives you a way. This is the basis for our ability to convert back and forth. If I knew x and y, I could get r from this equation. If I knew x and y, I could get theta from this equation, as long as I'm careful about taking inverse tangent. Notice I am not writing arctangent here, because arctangent has a defined domain, and I got to be really careful. In the other direction, and here's the vector decomposition stuff you guys probably have seen before, I could write x is equal to r times the cosine of theta. Y is equal to r times the sine of theta. That's what it means to sit on a unit circle, right? The coordinates of the unit circle are given by cosine and sine. And then you just stretch by a factor of r. So this conversion is a way to get from xy to an r and theta. And this conversion, if you knew r and theta, you could get the x and y values out that correspond. So here, if you start with an r and theta, you can produce an x and a y. I'm sure now I'm probably doing this backwards in the book. It says theta r all over the place, but this is the way I've learned. So I'll fix it in the future if I need to. It doesn't really matter as long as you're consistent. I guess theta makes more sense as an independent variable in the first slot. So let's practice. See if we can come up with a way of writing down a Cartesian equation from a polar equation. Okay, so suppose I give you a, yeah, I mean, I guess the idea here is you write down, so the simplest sort of question you can be asked about polar equations is always a test that you've been paying attention, which is if I tell you that I'm looking at the point, say, 2 pi over 3 in polar, find the Cartesian coordinates. Then you just feel like you're back in trigonometry again, right? Because this means this side of the triangle is 2. This angle is 2 pi over 3. So you can derive this directly from the conversion equations, or you can do it with the right triangle geometry. It's up to you. You're going to get the same answer either way. X is equal to cosine of 2 pi over 3. Y is equal to sine of 2 pi over 3. Or you can solve this right triangle here with a pi over 3 inside, and just keep in mind that you move to the left to find your x coordinates. Some people learn it this way, where you do it directly from the triangles. Right? So this is more like the physics approach, is you set up a triangle and you just keep track of the fact you move left and up, which tells you what the sign of the x and the y must be. Okay, so why do you care about knowing your trig angles? Because it's much easier to plot what's going on in a function if you can evaluate something like cosine of 2 pi over 3. Okay. So express x squared plus y squared is equal to 1 as a function in polar coordinates. So of course I know that x squared plus y squared is equal to 1. Circle, radius 1. Not a function, so this is an issue, right? So this set of this relation is the relation that defines the circle. All the points that make the circle up satisfy this relation, but I can't think of one of the other variables that's independent because it's not a function. It fails the vertical line test. But in polar coordinates, I do get a function, an actual function. The issue is this is not a function. Because circles are not natural in Cartesian coordinates, but in polar coordinates, circles are natural. So if x squared plus y squared is equal to 1, then what is x supposed to be? R squared, sorry, r cosine theta squared plus r sine theta squared is equal to 1. I can substitute x and y into the equation to get a new relationship between r and theta. That's the goal here. To get a relationship, this is between x and y. I want a relationship that has only r's and thetas in it. R squared cosine squared theta plus r squared sine squared theta. R squared times cosine squared theta plus sine squared theta is 1. What does that equal to? 1. Cosine squared plus sine squared is 1. There's another way to do it. Yeah. This is so there. You can, if you notice that you have that in there. I'm trying to go like this. This always works. That doesn't always work, right? Because you can have x's and y's that don't have this relationship. So that gets you r squared is 1. That's just the same as r being equal to 1. So that circle, which is not a function and is horrible in Cartesian coordinates, if you want to work with it, there's square roots running all over the place. In polar coordinates, it's just a constant. It's the constant function. The function that has constant radius. No matter what angle you give me, I always have radius 1. So the argument for polar coordinates is if you're working on a system that rotates, circles become dead easy to work with. This is like a constant function because it has constant radius. Okay. Make sense? And that's the argument for polar coordinates. The argument for polar coordinates is I want to be able to handle things that involve twistings and rotations that you can imagine anything more complicated than this in Cartesian coordinates is going to be a nightmare of cubes and square roots and cube roots all mixed together, where if I can somehow use the fact that I've got change with respect to angle, I get a much more natural family of functions. The last one I'll talk about before I let you off to your weekend are things that look like this. Hey, guess. Okay, if you already know the answer to this one, like for sure, don't tell me the answer here. Does anybody actually have a guess as to what this is? Oh, it's just cosine by itself. I'm thinking of this as a polar function. Take an angle in, get a cosine of the angle out. Let's see. 0, pi over 4, pi over 2, 3 pi over 4, pi. What is the cosine of 0? 1. Cosine of pi over 4? Okay. Cosine of pi over 2? 3 pi over 4? Pi? at angle 0, we go out 1 unit. At angle pi over 4, we come in to root 2 over 2. At pi over 2, now we're at 0, which means we've done this. We started at 1, and our radius is decreasing to 0 as we get to this direction. Now what happens when we point this way? At 3 pi over 4, it says root 2 over 2, but backwards, which puts me down here. 3 pi over 4 is in this direction, but my radius was negative, so I have to go the other direction. If you put in, just to illustrate here, 5 pi over 6, the cosine of 5 pi over 6 is minus root 3 over 2. So in this direction, I have to go backwards this way to root 3 over 2, and I end up with, that's my graph. So between 0 and pi, this thinks we've got a circle. So a very natural thing to do is to build up functions of little rotations like this. Okay, this is the sort of object that we're going to be studying against. Functions that you derive from expressions that look like this. And if you want to play around with this, if you never have before, I encourage you to investigate functions that look like cosine of m theta, where n is some integer, and see the sort of graphs that you get out, because this is part of why we're doing this. All right, have a good weekend. Pretty flowers. Thank you. They are pretty flowers. Pretty flowers.